Hello, chemists! This is Ms. Placino, and you are watching lesson 4.4 on molecular geometry. In today's lesson, we're going to take the Lewis structures that we drew in the previous lesson and try to predict the three-dimensional shape of those small molecules. Most new chemists kind of have the habit of thinking of the molecules as being very two-dimensional, very flat. And that's not always the case. These have different three-dimensional shapes, and based on what we draw, we should be able to predict them. So, some goals for today's lesson. We're going to understand what the VSEPR theory is and how to apply it. That's really just a theory we're going to use to predict shapes. And then we're going to go through and just predict three-dimensional geometry of small molecules. And the molecules that we drew in the previous lesson, those all count as small molecules. So let's get into it. Okay, VSEPR, VSEPR Theory. It stands for Valence Shell Electron Pair Repulsion Theory. Well, let's break this down and see what this means. Valence shell electrons. So we're talking about the electrons that are furthest away from the nucleus. Oh, those are the ones that get involved in bonding. Pairs. Oh, well, we need a pair of electrons to be involved in a bond. Repulsion. Well, we're talking about electrons and how to arrange these bonds that consist of electrons. So they're going to repel each other. And this is just the theory we use to predict geometry. So basically, this theory states that shape is based on spacing pairs of electrons as far apart as possible. Well, that makes sense. Electrons are all negatively charged, so putting pairs of electrons close together generally isn't a great idea. They're going to repel and make the molecule unstable. And when it comes to predicting geometry, it doesn't matter if it's a single, a double, or a triple bond. They're all treated the same way in the VSEPR theory. So when you go to predict geometry, it doesn't matter how atoms are bonded together, whether it's a single, a double, or a triple. It's more about how many other atoms are bonded to the central atom and how many unshared pairs of electrons are on that central atom. So today's lesson is going to be pretty dry. I apologize for that, but it is what it is. It's more fun to apply it than it is to learn it. Okay, so you've got that chart in your workbook, and we're just going to go through the different shapes. Any guesses on what we might call these structures? Well, they're just kind of in a straight line. There we go. They are linear. You can have the most simple of linear molecules, just something that's two atoms bonded together. Something like HCl is a great example. And then you can make things a little bit more complicated. So when we look at the central atom, it's the one in red. We've got two atoms bonded to the central atom. We don't see any unshared pairs of electrons on our central atom. If you had to take an educated guess about that bond angle, it should be 180 degrees. And a great example of a linear molecule is carbon dioxide. Carbon would be at the center. It's got double bonds to either of the oxygen atoms. And that's what we mean in VSEPR, that it doesn't matter if it's a double, a single, or a triple. It's just the fact that carbon is bonded to two other atoms and has no unshared pairs of electrons. All right, let's look at the next one. It kind of looks like a triangle to me. You just draw the lines. That looks pretty flat. Yeah, we call this trigonal planar. Trigonal due to the triangle shape. Planar because it's flat. All of the atoms are on the same plane. So there are three atoms bonded to the central atom. No unshared pairs of electrons on that central atom. What do you think the bond angle would be? It kind of goes around in a circle, divided by 3. 120 degrees as a bond angle. And what type of molecules, what atom is most likely present if we have only 3 bonds on the central atom? Hopefully you're thinking boron. Something like boron trihydride, BH3, is a good example of a trigonal planar molecule. It is possible to take off one of those bonded atoms and replace it with an unshared electron pair. That's kind of what this little cloud with 2 dots in it is supposed to represent. It's an unshared pair of electrons. So it looks like, it's kind of like a bent molecule. Yeah, we call it bent. this case, we've got 2 atoms bonded to the central atom and that 1 unshared pair of electrons. Bond angles, they tend to be a little bit less than 120 degrees. That unshared pair of electron takes up a lot of space, and it kind of forces those bonded pairs to move a little bit closer together. So maybe you see something more like 117, 118 degrees. O3 is a good example of this. Ozone, we drew it in the previous lesson, and it takes on this structure. Central atom, 1 unshared pair of electrons, 2 bonded atoms. Okay, our next shape. This is called tetrahedral. Prefix tetra meaning 4, and there are 4 atoms bonded to the central atom. There are no unshared pairs of electrons. Our bond angles are 109.5 degrees. And a lot of our carbon-containing compounds are going to take on this geometry as carbon readily forms 4 bonds. So CH4, methane, is a good example of a tetrahedral molecule. Look, it's right here too. I can start taking those atoms and start replacing one of the bonded atoms with an unshared pair of electrons, and that's going to change the geometry. We're back to having like 3 atoms bonded to it. We used trigonal before to describe 3. We're going to use it again. This time, those 3 atoms aren't on the same plane. They're like below that red atom. It's kind of like a pyramid. So we call this Trigonal Pyramidal. 3 atoms bonded to the central atom. 1 unshared pair of electrons. We're going to see those bond angles kind of shrink a little bit as that electron cloud takes up a bunch of space and forces the bonded atoms closer together. NH3, ammonia, is a trigonal pyramidal molecule. 1 unshared pair of electrons, 3 bonded pairs. I can take off another bonded atom and replace it with an unshared pair of electrons. We end up with a geometry that we've actually used before. It's bent. In this case, we've got 2 atoms bonded to the central atom, 2 unshared pairs of electrons. We're going to push those 2 bonded atoms even closer together. So we use this like less than notation. And a lot of times that's like in the ballpark of 105, 106 degrees for a bond angle. So it's not crazy dramatic, but it is noticeable. What very important molecule that you're supposed to drink a lot of every day has this geometry? Yeah, water. And it's a good thing it does. We'll talk about why in future lessons. Put a star next to tetrahedral, trigonal pyramidal, and bent. Those 3 are really, really important. Okay. Next up is trigonal bipyramidal. I can think trigonal because we've got that 3. The prefix bi means 2, so it's like a pyramid up top and a pyramid below. In this case, we've got 5 atoms bonded to the central atom. We have no unshared pairs of electrons. We're going to have 2 different sets of bond angles here. If you kind of look at like around like the equator of the central atom, they're shaped as a triangle, so that should be 120 degrees. And if you look from the one up to the one out, yeah, that's going to be a right angle at 90 degrees. What element needs to be present, based on what we talked about in the previous lesson, to get a trigonal bipyramidal geometry? Yeah, if it's going to have 5 bonds, we learned that phosphorus can expand its octet. So something like phosphorus pentachloride would be an example of a trigonal bipyramidal molecule. If you want to take AP chemistry, they'll start taking away some of these bonded atoms and replacing them with unshared pairs of electrons to get even more geometries. I'm going to leave those out from this lesson. I want to make sure we've got the basics down, but leave the more advanced stuff for AP Chem. So the last shape, I should say, that we're going to talk about is this one. And it has an octahedral geometry. If you were able to kind of like, connect the atoms, you would see that this is like 8-sided, hence octahedral. So 6 atoms bonded to the central atom, no unshared pairs of electrons on the central atom. All of our bond angles are at 90 degrees. And if it's expanded its octet to form 6 bonds, we are looking at Yeah, some sulfur-containing compound. Sulfur hexafluoride, SF6, is an example of an octahedral molecule. Just like with the trigonal bipyramidal, we can start pulling off atoms, replacing it with unshared pairs of electrons, and coming up with even more geometries. But we're going to skip out on that at this point in time. Let's look at some practice problems. So the practice problems for shape and molecular geometry, they're back with lesson 4.3 practice problems. So we went through this in the previous lesson, and I told you that like these lower three boxes, shape, bonds, our molecule is, we'd get to later. Well, guess what? It is now later. What you need to try to do is match up your geometry, your Lewis structure, with the molecular geometry or the shape that molecule is going to be. If you've got to constantly flip back and forth in your workbook from practice problems to the page where like you have all that information written down, that is a definite sign that you've got a little bit more memorizing to do. It's just kind of matching stuff up. I've got my central atom, 4 atoms bonded to it, no unshared pairs of electrons. That's a tetrahedral shape. And unfortunately, it's unlikely that you can just like stare at that molecule and just think really hard and have the word tetrahedral magically appear in your head. So it is going to take some memorization and some repetition, just the way it goes. Ultimately, you should do enough practice problems where it just kind of comes like second nature to you. H2S. So 2 atoms bonded to the central atom, 2 unshared pairs of electrons. That is the bent geometry. NH3, 1 unshared pair, 3 bonded atoms. That's Trigonal Pyramidal. I'm just going to abbreviate. Let's go trig and not try. Trig pyramidal. H2O looks a lot like H2S. Yeah, that's going to have the same geometry. Bent. So not a whole lot of thinking involved with the three-dimensional shape or molecular geometry. You're just going to have to get the repetition in and make the identification. All right, we will wrap up there. Nice job today, chemists. Thanks for tuning in, and I hope you found this helpful.